C is equal to 4 and N0 is 3, yeah? Now, if by taking these values in the table, now draw the graph. And if you will draw the graph, this would be the situation. Here, it is not exactly 3, yeah? But it is depicting between 2 and 3. But you can move it. If you can draw your own picture and on 3, you can show, because there is a equality point, which is between 2 and 3, yeah? The graph is giving you that idea, okay? Here on 3, it is greater. Then where is equality? It is between 2 and 3, yeah? So it is, that's why it is depicting that point. That is equality. And after that, f of n is higher and g of n is lower. It is the opposite of that previous. And then here you can say, for all the values greater than 2, greater than 2, greater than 2 in the table, which means 3, yeah? According to the table, it means 3. Function f of n is always greater than cn square. For all values greater than 2, function f of n is always greater than this cn square. Huh? This is written here. And hence, which means I can represent this as omega n square. That means that omega n square represent what? According to this equation, f of n greater than cgn. It means g of n is what? If it is omega g of n, it is always lower bound. It is lower bound. So the running time can be this minimum value or higher, okay? This is what it means. So if something is written like that, omega n square, then omega means lower bound. So the running time of the algorithm can be n square or higher. Represents a lower asymptotic limit for the function this. With a constant c is equal to 4, n is 0, n0 is equal to 3 from the table. And such that this equation f of n is what? Greater than or equal to c of n according to the table for all values of n greater than or equal to n0. N0 is what? 3. And now, but here in this point, we are saying now this is proved by using general variable. Huh? Clear? Theta. Asymptotic tight bound. Big O is upper bound. Big omega is lower bound. This theta is what? There is no big or lower here. Huh? Big theta is what? Sorry. Theta is what? Tight bound. Tight bound means close to that, exactly that. Huh? Average case. Representing average case for the real life cases. Huh? Or you can say it is more close to your real world or your real data and your algorithms. And how we can say? We can say that the running time of our algorithm f of n would be equal to theta of g of n. In this way, how we can say mathematically? This is that f of n would be equal to theta g of n. What it means actually? It means running time of our algorithm would be theta g of n. This is what it means. And okay, this is what it means. Then how it would, how we can prove it, or how we can get it, or how we can find this average time of our algorithm. How we can calculate this? Theta is what? Average time complexity. How we can find this average time complexity of our algorithm? This is another statement to say this concept. And here you have to find if there are two constants, C1 and C2, and N0 is the same concept, okay? N0 is, you have to find N0, and then you have to find two constants, C1 and C2. And then the equation for this theta is f of n would be greater than or equal to C1 g of n less than or equal to C2 G of n. F of n would be greater than this and less than this, or greater than equal or less than equal to, for all values. Yeah, it is in between. which is exactly means it is in between. So when f of n is less than or equal to cgn, this is your big O. Huh? And when f of n is always greater than c1 cgn, this is your previous omega. Huh? It is that or not? It is that equation. If I will show you for your clarity, big O equation is what? F of n less than or equal to cgn. Huh? And here f of n less than or equal to cgn. And then f of n greater than this. So both concepts are there. And this means that this now our function f of n is what? It is in between the big O value and the big omega value. It is what it means. Huh? This also means that function g is a tight bound for the function f. Okay, we already know that this is a tight bound. This is a tight bound, fixed bound. Huh? Here tight means it is fixed between this and that. It is fixed between worst and best case. It is fixed between big O and big omega. I can use different words, but the meaning is still the same. So, according to this equation, we know that it will provide us upper bound and lower bound. It is in between upper bound and lower bound. We already know that. Now, this is the third statement. Upper means big O, lower means big omega. Uh, if it is equal, then it will also mean that it is same in the best and the worst case. If it is equal, suppose that it is equal, f of n is equal to this and equal to this. What it means? Equal to upper bound, equal to lower bound. It means its worst and best cases same. If you will explain this equation, then you will have these words. Huh? One aspect is that the f of n will have upper bound and the lower bound. And the other concept is it is same as the upper bound or the lower bound, or the best and the worst case is same. Explaining different aspects of the equation. So that is here. Now, if you will draw a graph for that, okay, this is your n0 now. And before n0, everything is possible. But after n0, this is your f of n. Your equation is around this f of n. So f of n and then cg of n is always higher, c1 gn is lower, according to your previous understanding. And then how you can write? You can write with this theta notation. This is the theta notation also mentioned here. Theta and then theta n square or theta n cube and whatever that inside between the parentheses, it would be called your time complexity for this case. Now take this 4n plus 1 is equal to theta n. Here, this is your f of n and this is your g of n. Our f of n is 4n plus 1. G of n is what? This. We have to find two constants here. And we have to prove this equation. F of n greater than or equal to C1 g of n less than C2 g of n for all n. And here, if you will find it by hit and trial, you are taking C1 is equal to 4 and C2 is equal to 5. We are not using constants here. Huh? Are we using constants here? We are using. Where is that constant? This 4n, this is C and this is G of n. Huh? This is C and this is G of n. Understood? And this is your f of n, according to the equation. And now taking values with 1, 2, 3, 4, if you will check that, and here you see that here f of n is greater than this and equal to this, but there is no less or what. And similarly, for 9, for this, f of n is greater than this, which is okay, greater than that, greater than this, and f of n is what? Less than this, which is this. And next, this equation is becoming true, huh? And for all the next number, this equation is becoming true. And here, f of n is greater than this and not less but equal. And here we have the equality sign, so it means n0 is this. It means n0 is this, because equal is not violating the condition. Equal is existing. Equal is existing here. So then this is n0. And we have these two constants. Now, okay, you can say by the graph, this n0 is equal to 1. And then after that, 5n, according to the table, 5n is always greater. And this is always less. And this is what 5n is always greater. This is f of n, this is 4n. And then you can theoretically say that we have seen that for all the values of n, this equation is true with constant C1 and C2. And it proves that 4n is equal to, we can write 4n is equal to theta of n. Okay. What is little o? We have seen big O. Big O is upper bound. F of n less than or equal to this. And when it is equal, that is the maximum. There is no value or running time higher than that. Okay. Upper bound is that equality. Little o is what? This would be a strict condition. You will not have equality here. F of n would always be less than order of g of n. Okay. That equality sign is now gone from the theory. Always less. Always less. Okay. When always less, it is now strict condition, huh? Little o. So function definition, f of n is order of g of n if for every positive constant c there exists n0, the same previous theory, f of n would be less than cg of n. There is no equality here. For all positive n's, well, hence this function f of n grows strictly slower than g of n. Okay. Okay, that equality is now gone. And if this would be the situation, then you can also represent your time complexity with little o, not with big O. Okay. And when you will write little o of n square, what it means that algorithm complexity is what? Always less than that. Always less than that, huh? F of n. Okay. Example of little o, f of n is equal to n and g of n is equal to n square. If it, simple example, f of n is n, equation for this is that, and g of n is n square. From the equations, but n is always less than n square. But first we have to know what are the numbers. Huh? Positive. For positive numbers, it is always, yeah, for any constant, whatever the constant you will take with g of n, that constant will go with g of n, cgn, either 1 or 2 or 3, any constant. For any constant, f of n will always be what? Less than g of n. It is true or not? You can put the positive numbers there. Yeah, because this is n and this is n square. The equation n square is higher than n. And for all positive integers, if and that positive integer c will multiply with this, it is already extra, and you are multiplying further into it, it will become extra than that. So that's why f of n will be theta. Therefore, you can write o, little o of n square. which means this n grows slower than n square. N square is always higher. So in this case, this f of n will never reach the growth rate of g of n. G of n will always be higher. So this is for the little o, and the only difference between big O and little o is big O contains the equality, and here it contains the equal concept in it, and in little o there is no equal concept, only less. Huh? For omega, the same definition. Equality is now gone. F of n is always greater. And the example is also easy, read it by yourself, and I hope that you can understand it. Only reversed. Now we are taking f of n is equal to n square and g of n, n. The previous example, this example, we are taking the opposite of it. And yeah, no change. And then it will automatically, now your f of n is n square and g of n is what? N. Now, what is this? Okay. What is algorithm complexity? Or the other thing is we can stop it here, and because here topic is changing. Just a minute. What is your uh, comment or feedback on that? This topic, if I will start, it is going. This is the same topic, okay? It is the subtopic. Okay. Different topic. This is different. This is different. When the CLO will be finished, then we will go with the lab. Have you studied some course with me already? Then you don't know my nature. Okay, okay. There was no lab. Yeah. Normally with algorithms, there is no lab, okay? But you are belonging to the old curriculum, and in the old curriculum, lab was existing. So with your design and analysis of algorithm, lab is there. But now this title in the new curriculum, it is algorithms and complexity, and there is no lab with it because it is a mathematical course. There is no lab needed for that. But in old curriculum, lab is there, then we can do something, no issue. Okay. We can do using a program. Yeah, yeah. Programs will start, no issue. Here you can see programs will start. I will give you only algorithm. You have to design their programs. Okay. This is not easy. Okay. This is the core course of computer science. So you have to make your mind that this is a mathematical course. This is not easy. Okay. When in future, when I will run different algorithms here, then maybe when the recursion will come, then the recursion will give you the repetitions in the algorithm, then you can lose your mind. Okay. And then maybe you will start abusing me, huh? But I hope not. So I don't know, but this is among the toughest courses in CS. Okay. But I will try my best to make this easy. Yeah, this easy doesn't mean that I will throw out some of the topics from the course. Yeah. I will try my best to give you the understanding. This first CLO is only more theoretically, okay? More theoretically with a little less mathematically. But the next CLOs, we will start from the next CLOs, we will start from the proper topics, and then you will see algorithms and algorithms in this course. There would be no mathematics like that you are seeing here, no, but algorithms, pseudocode, or sometime code. Okay, I think, let's take it for 10, 20 minutes, and then I will stop because we have sufficient time. Okay. So previous topic was about asymptotic notations, three notations. These notations you can use to calculate the complexities of the algorithm. Okay. Knowledge of calculating complexity is different thing. But finally, when you will calculate your answer, how you can represent it, that is those notations will help you. Big O, big omega, and theta. You will write your final answer for your complexity in these terms by using these notations. Now, the topic is algorithm complexity. Slowly, we will go on towards that direction, that how we can calculate the complexity of our algorithm. So, algorithm complexity. Normally, algorithm complexity normally means how we can calculate the time and space of some algorithm when the size of the input is increasing from lower to higher. Because the behavior of the algorithm can change when the size of the input will increase from lower to higher. Huh? That's why there is an essential need to know that what would be the behavior of the algorithm on this input size. And that algorithm is using what type of different resources? Resources is a general word. Resources is a general word. Algorithm can use some data structure. Some data structure you have to consider them when you are calculating complexities. Not all, some. There are some kind of, for example, when you are considering recursion, then you have to consider this, that you are have recursion, and recursion have a different approach in calculating complexities. So there are different concepts that you have to consider, and some are considered, some you don't have to consider. So that's why the word resources is used to cover all the concepts. What resources an algorithm will consume or will use? This, when you will calculate the complexity, you will get your answers. But normally, when you will calculate complexity, you will get your answer about time and space complexity of your algorithm when the input size is varying. What is the other benefits of this algorithm complexity? Okay, for example, helps in understanding the algorithm efficiency and scalability. Efficiency is still the same meaning. Efficiency is running time, huh? Efficiency is running time. Scalability means when you are increasing the size of the input, algorithm is handling that varying size of the input smartly or not. When the algorithm is handling that large size of the input, medium, small, all sizes, then you can say that your algorithm is scalable. Okay. Then you can say your algorithm is scalable. If you will sleep, you will not understand what it means. Okay. I will say these sentences only once. Huh? Lawal Marur, what you are doing? What you are doing? What is scalable algorithm? Scale? What is scalable algorithm? This is what I'm saying, okay? It is not possible for me to say these sentences again and again for each student. Some students who are sleeping now, and if they will become alive, I cannot say this sentence again. So anyhow, efficiency is a word that is normally used for the time complexity of the algorithm. But it depends on the context. Sometimes you can also include space complexity within the efficiency, but mostly it is used for the time complexity. But and the another word is scalability. What it means, when the input size of your algorithm is increasing from lower size to higher size. So small size, medium, higher, and then the behavior of the algorithm will change. And if the algorithm is handling this change in input size, handling handling this change effectively, with quality, smartly, then you can say that your algorithm is scalable and has this feature of scalability. Uh, so through this complexity, when you will calculate the complexity of different algorithms, then you can also compare these different algorithms on different input sizes. This is also a benefit of this complexity. Here, this slide is basically giving you that what are the benefits and use of calculating complexity. For example, there is one problem and four different people have provided solution for this problem with different logics. And then I will check. I will give different inputs to these solutions and I will see what is the behavior of these. Huh? And then I can also compare that which one is a better one. Hmm? This is what it means. And the last helps to determine the difficulty of a problem. Yeah. The algorithm is complex. That answer which you will give finally in the form of big O or big omega or theta, that answer will also give us a hint that this problem is complex or not. Okay. If if it is only big O of n means linear, huh? Then it would be simple. And if it would be order of n log of n plus e log of v, then it means it is something complicated, huh? Then it means it would be something complicated. Now, as we have to go understand the complexity, then the first we are going to, I mentioned it, time and space. And so first we are going with the time complexity. And time complexity is what time our algorithm is taking. That is what the time complexity of our algorithm in short words. Our algorithm, what amount of time it will take, this is called the time complexity. On the worst case, huh? Oh, sorry. I will. What is time complexity? The amount of time taken by the algorithm on a given length of input. And if we are talking about big O is also representing time complexity, but that would be with the maximum size. Hmm? You can say with the maximum number of operations. Size is not, leave it behind. Huh? How can we calculate? There are different rules. Now I think, yes, we will see these rules one by one. The first, how the time complexity can be computed? This is rule 1. This is 2. This is 3. And this is now, this would be the example. In your algorithm, you will have lines of statement. Huh? In your algorithm, you will have lines of statement. I can call it instructions. I can call it instructions. So then you have to do what? You have to calculate the cost of each fundamental instruction. You have to calculate the cost. Each instruction will have some cost. Each instruction will have some cost. And you have to calculate the cost of each statement or each instruction. And if that instruction is repeating 50 times, you have to calculate that cost 50 times. Okay. For example, there would be some statement under a loop, and loop is executing 50 times. And if that statement is taking cost 1, then the loop is executing 50 times. So 1 plus 1 plus 1 plus 1, 50 times you have to add. You have to add that 1 50 times. This is what it means. You have to, and the number of times the instruction is executed. You have to calculate the cost accordingly. Rule number 1. This rule is for the, if in your algorithm you have a comparative statement, num1 equal to num2, comparative statement, huh? Containing less than equal to, greater than equal to conditions. So if in your statements you have a comparative statement like this, a equal to 5, comparative statement, huh? If a equal to 5, this is a conditional statement, comparative statement. And if your code or pseudocode has the return statement, there is no, yeah, this is the return statement here. If your code has the assignment statement, this is assignment statement, a is equal to 5, assigning some value to some variable, assignment statement. Or you are reading a variable, or you are taking some value into variable. Is we have a variable? No, we are not reading. Huh? We are reading a variable. Do we have? No. That reading can be into the form of input. For example, I can say C is equal to A plus B. So A plus B is what? You are fetching, reading value from that variable. Huh? But actually it is due to equal operator. It is what? Assignment statement. So this statement can be assignment statement, can be reading a variable, but it is not reading. If I will say here, C here, then it is reading. Huh? But anyhow, then it is clear reading. Huh? Okay. I have mentioned here, okay, this is assignment or reading variable. This is return, comparative, assignment. If you have these things in your algorithm or code, then you have to take the cost of each instruction as order of 1. And here you have order of 1. What it means? Worst case. Worst case cost would be order of 1 for that statement only. So what it means? It means for int a is equal to 5, what is the cost for worst case cost for it? Order of 1. And if a is equal to 5, what is the cost for it? Order of 1. Order of 1. And this is also comparison here due to this. And also assignment is mixture, order of 1. Just for a whole statement, just say order of 1. This is also assignment, order of 1. I can say order of 1 plus order of 1. 1 plus 1, I can say, but it is again a constant. Huh? And at the end, you have to ignore all the constants. You have to throw all the constants from your equation, from your summation. Anyhow, I will do this next. And then, for example, if you have this is a rule. Here we are saying statement 1, statement 2, statement 3, statement 4. Huh? We are saying statement 1, statement 2, 3, 4. Huh? And then you have to do what? What is the cost? What is the time for statement 1 plus time for statement 2 plus and so on time for statement n? You have to add all these times. And then you will have a total time for your algorithm. And if it would be order of 1 for statement 1 and order of 1 for 2 and so on for 3 and 4, then it would be 4, maximum 4. Huh? For this previous statement, it is what? It is maximum 4. Order of 1 plus order of 1 plus order of 1 plus order of 1. Maximum it is what? Or you can simply write 1 plus 1 plus 1 plus 1. Maximum 4. Or finally, you can say order of 4. Due to these 4 statements. 1 plus 1 plus order of 4, nothing else. And 4 is a constant. The total time for this module is order of 4. If so, this statement, we can also write this statement shortly like that. Mostly in algorithmic books, you will also see that total time is represented with the T of n. Total time is represented with T of n. You can also represent this T of n with F of n that you have seen in the previous slides. F of n, huh? Okay, T of n. And then this time we are representing it with small t, and this statement again, plus this time we are representing it with small t. So this can also be written in some literature like this. Meaning is same. And it would be order of 1 plus order of 1 plus order of 1 plus order of 1. For previous example, it would be it is giving you what? It is finally giving you T of it is finally giving you the time after summation. What time? T of total time, T of 4 for this example. Understanding? And this T of 4 finally I can write in big O like order of 1. This is the normal way to represent. If you want to represent constant time of an algorithm, you can represent it in order of 1. Okay, now here, rule number 2. If you have a loop, in your algorithm or code, then first you have to find the running time of your body of the loop. In the body of the loop, you can have one statement or multiple statements. And if it is multiple statement, you know how to calculate the statement by statement cost. Huh? Calculate statement by statement cost and sum them up. And then you will have the time for the body of the loop. And then you have to check how many times that loop is executing. If that loop is executing n times, multiply that cost of the body of the loop n times. Multiply n times. And then you will have your final total time. So if we have a loop, we have to find out the runtime of the block inside. For example, here this is the loop, and these curly brackets are showing that this is the body of the loop. So this is the block. So you have to find the runtime of this. This is a cout statement, so order of 1. Huh? This is just one statement. Huh? Just one statement. Printing something, order of 1. So you have to find out the runtime of this block, which is runtime, and then multiply it with the number of times the program is repeating that loop. And this loop is doing what? I is equal to 0, I less than n. If n is 10, then you have to multiply it with 10. But theoretically, mathematically, when you are calculating, you are not, if this is the last value that is given in the in the algorithm. For example, input size is 10 and this is 10. If n is 10, then you normally, mathematically, theoretically, you are multiplying it with n. Okay. So T of n, what according to this statement, or according to this statement, what would be the formula? T of n for this would be T, and this is C out statement, C out statement. T is what? Time for this statement, which is order of 1, which is order of 1, multiplied by this n. N is the number of times this loop will execute. And this is what? When you are multiplying it with n, n multiplied by 1, mathematically, n multiplied by 1, what answer you will have? N. Hmm? If I say 4 multiplied by 1, what answer you will have? 4. But here we are writing it generally, n multiplied by 1. So then order of n. And if it is order of n, this is called linear complexity. Okay. This is whatever the input size, if the array is containing 10 elements and you will get the complexity also order of n, it means for 10 elements. Anyhow, this is how, if there is a loop, how you have to calculate cost. Now you know that, huh? Calculate the block, cost for the block, and multiply with the total number of repetitions of the loop. Yes. As long as you difference how to count that Python loop of Python. No. There's no difference. Same. Yeah. Algorithm is not dealing with the code. Okay. Algorithm is, so listen, algorithm is the first step. What is the definition? Step by step procedure to solve the problem. Not writing the code. Writing the code is after that algorithm. So, okay. So there is no question to say that the same for the Python loop or for the C++ loop. No, here we have the loop. Whatever the loop is written, loop means total number of repetitions. Okay. Now, if you have two-dimensional array, and then to deal this, you need nested loops. And if you have these nested loops like that, I is equal to 0, I less than n, I plus plus, and j is equal to 0, j less than m, j plus plus, and the statement is also again the simple statement. This is one internal loop, and then this is the external loop. How you can calculate the time complexity for this small code? Again, C out statement. How many times this loop is executing? M times, huh? So then multiply it with M. And then this, now this M multiplied by T is the time for this block, huh? Including for loop. This, or so this would be the time something here, and then this, when you multiply it with this M, then it means that this is the time for this whole block. And this block is under this for loop, and what is the time for that? N. N time repetition. So multiply this block with the N. So now this is the formula, N multiplied by M multiplied by T, C out statement. And for C out statement, you have order of 1. So you have to multiply with M, you have to multiply with N. So N, M multiplied with 1 and M. So finally, order of, you can write N, M, or finally you can write N, M like that, or you can write N multiplied by M, whatever you want. And this is called quadratic complexity. Why it is called quadratic complexity? Because if I say, sorry, N is equal to 2, this 2 means quadratic, huh? And then how I can write? I can write N, I can write it like that, N multiplied by N, huh? I can write or not? I can write or not algebraically. This n plus 1 will become 2 and it is equal to this one. Huh? That's why, and here nm, which two things are multiplying, and here two things are multiplying. So that's why we are calling it quadratic complexity. When you have something complexity big O and M, two things are multiplying, you can call them quadratic. This is the name for the quadratic. And here, let's see this example of binary search. And here, in algorithm, we are calculating statement by statement time complexity of this algorithm. We are not thinking that what this algorithm is doing, okay? We are not thinking that what this algorithm is doing. Structurally, what is the structure of this algorithm? We only have to look over it, and then we have to calculate the cost of each statement, finally sum them up, and then finally ignore some values. So here, this is the algorithm for the binary search is given. Just last slide, okay? I don't want to start, but uh, if you will keep all these concepts that I have given in the previous slide in your mind for the next lecture, then I can stop it here. Is it okay? You will keep these things in your mind, huh? So that in the next lecture, I don't have to revise previously. Okay. Then we are stopping here.